Hi guys, today we will start with the Avl trees. So what is this Avl tree? Why we have to go with the Avl tree? All these things we will be covering. So Avl tree was invented by three scientists, Edelson, Welsky and Lindas. These are the three scientists who invented Avl tree. So why it became Avl is the first name of the first scientist, first letter. So this became Avl tree. So what is this is Avl tree is it is a type of a binary search tree. Already we know what is meant by a binary search tree. So binary search tree property is first it should be a binary tree. The property of a binary tree is at most two children. At most two children means it can be 0, 1 or 2 children we can have for a particular node. And coming to binary search tree is the left node value will be less than the root node and the right node value will be greater than the root node. So if you take this example, this is a binary search tree. So 70 is a root node, and if you take the left child, 60 is less than the root. And if you take the right child, 80 is greater than the root node here. And similarly 55 is the left child of 60, so it is less than the root. And 77 is a left child of 80, again it is less than here. So Avl tree should satisfy the property of binary search tree. Now I'll just why we have to go with the Avl tree we will see. Then we will see what are the properties the Avl tree should satisfy. First property is it should be a binary search tree. So already we know what is a binary search tree. So now here we'll take the example. Let us take the example the binary search tree for months of a year. Now this is a binary search tree we have. Now for this binary search tree, if you find out the average number of comparisons, let us find out the average number of comparisons. So if you want to search January, if you want search January, then the number of memory access for January is 1. The number of memory accessing is January is 1. Now if you want to search for February, 1, 2, 2. And March, 1, 2. April, 1, 2, 3. Similarly, next May, 1, 2, 3. June, 1, 2, 3. July. So in this way, you will be calculating the comparisons. That means you will be seeing how many comparisons are required to search each and every element. Now for this I will take the average. So if I take the average, I am getting 42. 12 months are there. So 42 by 12, it is the 3.5. So 3.5 is the average number of comparisons for this binary search tree. Average number of comparisons we are getting is a 3.5. Now the same, we will take one more variation of the same type of the months and let us check what will be the average number of comparisons. So this is one more binary search tree we have. In the same way, let us again find out the comparisons for searching January 1, 2, 3. For searching February 1, 2. For searching, for example, June 1, 2, 3, 4. June. So in this way, for each and every month, if you want to search, let us write down all the things and you add all the searches, and by 12 you are getting 3.1. 3.1 comparisons you are getting. For the first binary search tree, you are getting 3.5, and for this binary tree, you are getting 3.1 comparisons. Now, the same thing if you are arranging in the lexicographic order. Lexicographic order is nothing but in the alphabetical order. If you arrange these months in the lexicographic order, that is in the alphabetical order, then this you have. So first A, next August. So August, AU, both A, U is afterwards after P. So based on the alphabetical order, if you see, the tree will be growing towards the right hand side. The tree is growing towards the right hand side here. And again, if you try to find out the comparisons, average number of comparisons, for April it is 1, for August it is 2, it is 3. If you want to search for December, if for April it is 1, for August 1, 2, for December 1, 2, 3, 3 comparisons. So if you go on if you find out, if you want to search all the months, then you add and divide by 12, you will be getting 6.5 comparisons. So the same months, the 3 different you are getting. This is 3.5 and this is 3.1 and another one you are getting is a 6.5. So that is the drawback you have with the binary search tree. So binary search tree, if you see here, if you are arranging in the lexicographic order, you are getting like big O of n is a complexity you are getting. That is, you can say it has like 12 comparisons you are doing here. 12 elements you have, you are doing the 12 comparisons. So the complexity is big O of n. So in the binary search tree, if you want to search an element, it is taking big O of n complexity here. So to reduce the search time, now what we are doing is we are going with the Avl tree. So that comes the necessity of Avl tree. So now we will see what is the property the Avl tree should satisfy. So already I said the Avl tree, first one of the property is it should be a binary search tree, and another property is it should be height balancing tree. It should be a height balancing tree. This is another property. First property is this and the second property is this, height balancing tree. So what is this height balancing tree? Nothing but we have to find out the balancing factor. For each and every node in a tree, we have to find out the balancing factor. So how to find out the balancing factor is height of left subtree minus height of right tree. Height of left tree minus height of, like for example, if I want to find out the balancing factor for 70. Now how to find out for 70? The height of left subtree minus the height of right subtree. So the height is nothing but how many children you have in the left? 2. And how many children you have in the right for 70? 2. So 2 minus 2, it is 0. For 70 it is 0. Now if I want to find out for 80, for this I want to find out the balancing factor. So how to find out? The left child is 1 and I don't have the right child. So 1 minus 1, 1 minus 0, because I don't have the right child here. So 1 minus 0 is 1. So this, for this it is 1 and for this it is 0. Now for example, if I want to find out for 77, I don't have the left child and I don't have the right child. So 0 left and 0 right, so this becomes 0. Similarly, this is also 0, and if I want to find out for 60, I have left is 1, I don't have the right, so it is 1. So balancing factor we should find out for each and every node. Then how you can say it is a height balancing tree is every node should have either the value minus 1 as a balancing factor, or it should have 0 as a balancing factor, or 1 as a balancing factor. So these are the 3 things only we have. So that is nothing but the modulus of left subtree height minus right subtree, that is less than or equal to 1. So since I have taken modulus, even minus 1 also you will be considering as plus 1 here. So these are the 2 factors one should have. It should be balanced. Another one is it should be height balancing. So we will see the examples for this. Now I want to check whether this is an Avl tree or not. So to check this is an Avl tree or not, what I said, we have to find out the balancing factor. If one of the node is not satisfying, then the complete tree is not an Avl tree. So for example, if I want to find out for April. Now for April, do we have left children? No, we don't have the left children here. Do we have right? Yes, we have 2. So here for April we are getting 0 minus 2, it is minus 2. But for balancing factor, what are the values we should have? It should be minus 1, 0, 1. But what you have here? You are getting minus 2. So you are getting minus 2, that means it is not an Avl tree. So this is not an AVL tree. Now coming to this one. Now is this an AVL tree? Yes, this is an AVL tree. If you want to find out for any node, it will be satisfying. For example, if I want to find out for August, the left is 1 and the right is 1. So 1 minus 1, 0. Like for example, if I want to find out for February, 1, 2 and 2 minus 1, 1. So it is 1. So if you find out for any node, this will be the balancing factor will be the value either 0, 1 or minus 1 only. So it is a AVL tree. So I have just shown you here. This is A is the first figure, B is the second figure. Now if I want to find out whether it is an AVL tree, now for example, if I want to find out for November, I want to find out for November. So left children 0, or how many right children you have? 2. So 0 minus 2 minus 2. So it is not in the range. So this is not AVL tree. This is not AVL tree. So if the trees are AVL tree, then definitely the searching time will be reduced. So now we will see how to make the tree as a AVL now. Now let us see the first operation, insertion. So how we have to insert now? Insert an element into an AVL tree. So insertion is similar to binary search tree. Here if it does not maintaining the balance factor, then we do rotations. Insertion, how we have done the insertion in the binary search tree. What is the property? If you have a node less than the root, we will be inserting in the left. If you have a value which is greater than, then we will be inserting in the right. So based on the same property, we will be going for insertion. But always we have to see that it is satisfying the property of balance factor. If it is not satisfying the property of a balance factor, we do the rotations here. So we will see what are the rotations now. So we have the 4 rules for insertion here. So that is left left, left right, right right and right left. These are the 4 rules you have. What is this? I show you with an example. Now these are the values what we have, and 5, 8, 9, all these are the values what we have. Now all these values we want to go for insertion. So how we have to go for insertion? I said insertion you will be doing similar to the binary search tree. Now what is our first value you have? I have given the numbers for the figures here. So A. Now what is the first node you have? 5. This 5 you have inserted. Now whenever you are inserting, I said we have to check the balance factor. Do we have a left child? No. Do we have a right child? No. So 0 minus 0, 0. So the balance factor for the node 5 is 0. So we have completed 5. Now come with the insertion of 8 now. So when you want to insert 8, you have to check with the root now. So 8 is greater than 5. That becomes the 8 becomes the right child. So now you have inserted. As already I said, whenever we are going for insertion, always it should satisfy the property of a binary search tree, and it should satisfy the balance factor. Okay, it is satisfying the binary search tree, and let us find out the balance factor. Now for 8, we don't have the left and right, so this is 0. Now coming for 5, do we have left? No, left is 0 and the right is 1. So that is 0 minus 1, but since we have a modulus, even a negative value also, you will take it as a positive. So with this 8 we completed. Now come to the 9 now. So 9 is greater than 5. So since 9 is greater than 5, you have to insert in the right side of the tree now. So 5, 8 and 9 is greater than 8. So this becomes again the right child now. So again find out the balance factor. For 9, no left child and right child, this is 0. And this is 1 right child you have, we don't have left child, 1. And coming to 5, we don't have the left children. So this is 0. And how many you have here? 2 children you have. So 0 minus 2, it is minus 2. And since it is a modulus, we will take it as 2 only. So Now this tree is not satisfying the property of Avl tree. We don't have it is not satisfying the balance property here. So it should be either 0, 1 or -1 only. Now, since it is not satisfying, what I said, we have to go with the rotation now. So, how to do? I said we have 4 types of rotations now. So, which rotation we have to apply? Now, if you see the tree here, if you observe the tree is growing towards which side? The tree is growing towards right and again right. The tree is growing towards right and right. So, this case is a right case. Right case. If it is a right case, what we have to do is we have to go for left rotation. If it is a right, why right? Because the tree is growing towards the right side here. If it is right, we have to go with the left rotation now. So, here we have a problem. So, in between these two, whatever the node you have, that node you have to go with the left rotation now. So, this we have to go with the left rotation. So, when you go with the left rotation, now this will be rotated, this will be rotated. Now, 8 will become the root and the 5 will come here. Since it is right, what you have to do, I said, we have to go with the left rotation. So, this you have to rotate now. In between these two, whatever the node you have, that you have to rotate now. So, this is after rotation you have. Now, again, after rotation, let us check the balancing factor. Again, this is 0. Now, this is 0. So, now this is satisfying. So, we have completed 9. Now, come to 3. Now, you want to insert 3 now. So, 3 is less than 8. So, it will be coming to the left now. So, again find out the balancing factor. Yes. So, everything is satisfying. So, no rotation is required. Now, 3 also we have completed. Now, come to 2. Now, again you compare. 2 is less than 8. That means we have to go with the left side now. So, 2 will be the left child of 3. Now, once again find out the balancing factor. So, if you find out the balancing factors, here these are the factors we are getting 2, 2, 1, 0 and 0. These are the balancing factors which are not satisfying. This is not satisfying and this is not satisfying now. So, when you have two things here which is near to the leaf node, you consider that. Which is near to the leaf node? The 5 is near to the leaf node. Now, we have to see the case here. Which case you have? 5 and 3, that is towards the left side you have, and 2 again you have towards the left side you have. Left you have here. So, left means which side you have to rotate? Right you have to rotate. So, between these two, whatever the node you have, you just rotate the right side now. That means this 5 you have to rotate to the right side. So, now 3 will come here and the 5 will come. So, 8 and 9 will be same as it is. Now, the 3 should be rotated right, I said. So, now this 5 is coming here. Now, once again find out the balancing factor. So, find the balancing factor. Now, everything is satisfying. So, we have completed 2. Now, what is the next when you have 12? So, 12 is greater than 8. That means it comes to the right side now. So, 9 right is becoming 12. Now, find out the balancing factor again. Yeah, everything is fine. No need of any rotation. So, 12 also done. Now, coming to 18. So, 18 is again greater than 8. So, again it will come to the right of 12. So, once again you check the balancing factors. So, if you do the balancing factor, for this node it is not satisfying. So, 2 we are getting here. Here it is not satisfying. So, now you have to see which one it is. Which type of rotation we have to apply. So, this is right and right. So, again we have is a right. So, if you have right, what we have to do? We have to go with the left rotation. So, if you have right, we have to go with the left rotation. That means we have to rotate left now. So, now this 9 will come here. So when you're rotating, this part is as it is and you're rotating left. Now again check the balancing factors, so everything is satisfied now. So that which one we have done, 18 we have completed. Now come to the next one, 6. Let us insert 6 now. So 6 is less than 8. So since it is less than 8, you go with the insertion as for the left, and this you have inserted 6. So once again you check the balancing factors. Yes, it is satisfying, so no need of any rotation here. So 6 we have done. Now what's the next value you have? 11. So 11 is greater than 8. So that means it should come to the right side now. So right side, that is 9 right will become 11. 9 right is 11. So again check the balancing factor. Yeah, it's satisfying. No need of any rotation. So this 11 also we have done. Now come to the 10 now. So if you see 10 again, what is 10 is greater than 8. So since 10 is greater than 8, that means we have to insert towards the right now. So that means now 11 left will become 10. 11 left is becoming 10 now. So once again find the balancing factors. So if you check the balancing factors here, this we have 2 and this we have 2 here. So 2 things are violating. So for that I said which is near to the leaf node, let us check that. Now how you have a tree growth now? One is towards the right you have, and again you have left here. That means this case is a right left now. Right left. So for right left, what we have to do? Yeah, I'll say for right left. So now here we are getting the case of right left now. So when you are getting right left, first what we will do here is the left part what we have, that we will change it to right now. So this is the left you have, right? This is the left you have. Now this left, what we will do is we will change it to, we will move in the opposite direction. We will change it to the right. So this left, whatever you have, you change it to the right now. So nothing I have done here. Now what I have done, this I am changing into right now. So when I change into the right, now you see, this is the thing what we are getting. Now after changing into the right, you have the case of right now. You have the case of right. So right means what we have to do? Right, we have to change into the left. We have is a right left. So this, whatever the left part you have, that you change into the right. You change into the right. Then it is converted into right now. So if it is a right, already we know we have to move left. So now this you move it left. So when you move it left, now this is the case. Now this 9 will come here. So now if you check the balancing factor, everything is satisfied. Only the problem here you will be getting is if it is a right left, what I have said, this left you move it, make it as a right, and already you have right, so it will become right. So if it is right, then you have to make it as left. Now what will another case? If it is a left right, this right you make it as a left, already you have left. Now left you know, if you have left, move right. This is the thing you have to do for these two cases. We'll see the another example also.